We often think chemistry is, super complicated, like just labs and bubbling
Yeah.
beakers.
Right. White coats and safety goggles.
Exactly. But have you ever thought about how you're doing chemistry when you cook, or even just how the air feels different when it gets cold?
Uh-huh. It's everywhere.
Yeah, even this book we looked at, Chemistry for Kids, it starts right out saying chemistry isn't some abstract thing. It's actually something we do, kind of instinctively sometimes.
That's such a great point to start with, because fundamentally, chemistry is just the study of, well, stuff, matter, and how it changes,
The stuff that makes up everything.
pretty much, and how that stuff combines,
Mhm.
transforms, all of it. It's what this beginner's guide is all about, making it understandable.
Okay, so that's what we're going to do today. We're going to dive into some of those core ideas from Chemistry for Kids.
Yeah, give you a clear, hopefully engaging look at the basics.
Think of it as your quick guide to understanding, well, almost reality itself.
Huh. Yeah, no big deal. But our goal really is just to walk through these foundational concepts together.
So where do we start?
We'll kick off with matter itself.
Yeah.
What is it? What forms does it take? Then elements versus compounds. What's the difference?
Okay.
And then we'll get into the really tiny stuff, atoms and molecules,
Mm.
and how they interact, how they change.
All right, let's do it. Starting with matter. What actually is matter?
Okay, so the book defines it pretty simply.
Mhm.
Anything that occupies space and has mass.
Occupy space has mass.
And what's interesting is this includes things you might not immediately think of as having, like weight. Air, for instance.
Air has mass. Right. Okay.
Does. Even light, according to the source, fits this definition.
Huh. That's unexpected. A sunbeam has mass.
Well, it occupies space and has energy, which relates to mass via EMCO, but yeah, it's considered in this context.
Yeah.
And in this matter, it exists in different forms or states.
Right. Like solid, liquid, gas. I learned those in school.
Yep, those are the main three we experience. And the book adds a fourth.
Plasma.
Ah, yes, plasma.
Yeah.
So solids first. They have a definite shape, definite volume. Think wood, stone, sand. Pretty straightforward.
Got it. It doesn't change shape easily.
Exactly. Liquids, then, have a definite volume, but they take the shape of their container, right? Water, oil.
Yeah, pour water from a glass to a bowl. It changes shape, but it's the same amount of water.
Precisely. Then gas. No definite shape, no definite volume. It just expands to fill whatever space it's in. Air, helium in a balloon.
Fills the whole room or the whole balloon.
Okay.
And plasma. That one always sounds a bit sci-fi.
It does. And the book points out it doesn't really occur naturally, like right here on Earth in everyday situations.
Oh, where is it then?
It's mostly in outer space. Stars, like our sun, are basically giant balls of plasma. Think of it as super, super hot gas where the electrons have been stripped from the atoms. It's got charged particles.
Whoa, so high energy stuff.
Extremely high energy. But we can make it artificially here. Lightning is a natural example on Earth, actually. And neon signs, the glowing gas inside, that's plasma too.
Okay, so solid, liquid, gas, and the high energy one, plasma. Mostly out in space or in things like lightning.
Huh.
Got it. Now, this matter, it's made of elements and compounds. You mentioned that.
Yep. That's the next layer down. What is all this stuff made of?
So what's the difference? Element versus compound.
An element is like the purest form.
Yeah.
You can't break it down into anything simpler using chemical methods. Gold is just gold atoms. Oxygen is just oxygen atoms.
So the things on the periodic table.
Exactly. Those are the elements. There are about 118 known now. Earth has about 98 naturally occurring ones.
And that table was put together by Mendeleev, right?
Nature and life, yeah.
Yeah.
He did some crucial early work organizing them based on their properties. Really fundamental stuff.
Okay, elements, basic building blocks. What about compounds then?
Compounds are what you get when two or more different elements join together chemically. They bond.
Ah, like water.
Water is the perfect example. It's H0. Two hydrogen atoms bonded to one oxygen atom. It's not hydrogen anymore. It's not oxygen anymore. It's a new substance, water, with totally different properties.
Right, and understanding that difference is key.
It's crucial because chemical changes are all about elements rearranging and forming new compounds or compounds breaking down.
Makes sense. Okay, so matter has states, and it's made of elements or combinations of elements called compounds. But what are those made of? Like the absolute smallest level.
Now we're getting down to it. Atoms and molecules.
Finally.
So an atom is the smallest possible piece of an element that still is that element. Like one single atom of gold is still gold.
Okay, the fundamental unit.
Right. And atoms themselves are made of even smaller things. Protons, electrons, and neutrons. You probably remember those.
Vaguely. Protons positive, Electrons negative, neutrons neutral.
You got it. And here's the really critical part. The number of protons determines what element it is. Change the number of protons, you change the element completely.
Wow. So add a proton to, say, hydrogen, and it becomes...
Helium, just like that. The number of electrons can change too, which makes ions charged to atoms, and that's super important for bonding, which we'll get to.
Okay, so atoms are the element's smallest unit, defined by protons. What are molecules then?
Molecules are just groups of atoms. Two or more atoms stuck together by chemical bonds. They can be atoms of the same element, like an oxygen molecule,
Yeah.
ORO, which has two oxygen atoms bonded.
Or different elements, like water, HO.
Exactly. HO is a molecule made of three atoms, two hydrogen, one oxygen. And the number of these molecules you have affects the volume of the substance. More molecules, generally more volume.
Okay, atoms build elements, atoms bond to make molecules, which make up compounds, or sometimes elements like O. Got the pieces.
Right.
Now, how does this stuff change? The book mentioned physical versus chemical changes.
God, this is a key distinction. A physical change alters the appearance or state, but not the actual chemical identity.
Like melting ice.
Perfect example. Ice melts into water. It looks different, feels different, but it's still HO molecules. The composition hasn't changed.
Or crushing something, like a can.
Yep. Still aluminum, just dented. Or dissolving sugar in water, at least initially. The sugar molecules just spread out in the water. That's physical. No new substance is formed.
Okay, so physical change, same stuff, different look or state. What about chemical change? The book called it a chemical reaction, too.
That's where things get really interesting. A chemical change, or reaction, is a process that creates a new substance. The atoms rearrange, forming new molecules with different properties.
Like burning wood.
Classic example. The wood reacts with oxygen. It doesn't just disappear. It turns into ash, smoke, carbon dioxide, water vapor. Totally different substances with different atomic arrangements.
The atoms are still there, just bonded differently.
Precisely. They've rearranged into new combinations.
Okay. The book had a couple of experiments to show this, right? Dissolving salt versus sugar.
Yeah, that was a good one. You put salt in water, sugar in water, wait an hour.
And what happens? Or what should happen?
Well, the salt seems to disappear, right? Dissolves. The sugar might too, but the book suggests some might settle out again.
Okay, so how does that show chemical versus physical?
Here's the explanation the book gives. Salt, sodium chloride, is an ionic compound. When it dissolves, the water molecules actually pull the sodium ions and chloride ions apart. They interact chemically.
So it's not just floating around, it's interacting.
Right. The ionic bonds are broken, and new interactions form with water. The book calls this a chemical change and gives a rule. Ionic compounds often react chemically with water.
Huh. Okay. What about the sugar then? Why does it settle?
Sugar is different. It's a covalent compound. Its molecules don't break into ions. They just spread out among the water molecules. They disperse.
So it looks dissolved, but it's just mixing.
Essentially, yes. It's a physical change. Given time, the intact sugar molecules can settle back down because they haven't fundamentally changed or bonded with the water.
Okay, that's clear. Salt, chemical interaction, sugar, physical dispersion. Then there was a second experiment, boiling these solutions.
Yep. Boiling the salt water versus the sugar water.
What happened there?
With the salt water, you boil it, the water turns to steam. That's a physical change, liquid to gas. But the salt ions, they get left behind.
And they just become salt crystals again.
Exactly. The sodium and chloride ions recombine as the water leaves. You get your salt back. Because you can separate them just by boiling off the water, and you could condense the steam back to water, it's considered a physical change overall for the salt itself.
We recovered the original stuff. Now, boiling sugar water. The book mentioned caramel.
Ah, yes, that's different. When you boil sugar water and keep heating it as the water boils off, the sugar molecules start to break down.
Break down how?
Through chemical reactions like oxidation. The heat causes the sugar structure to change, new molecules form. That's what gives caramel its brown color and distinct flavor. It's not sugar anymore.
It's a new substance.
Totally new substances are formed. If you keep heating it, you'll eventually just end up with carbon, basically black char. That's definitely a chemical change. The original sugar is gone.
Wow. Boiling salt water, physical separation. Boiling sugar water, chemical transformation. That really makes the difference clear.
It does, doesn't it? Simple experiments, but they illustrate a core concept.
Okay, so we've got matter, states, elements, compounds, atoms, molecules, and how they change physically or chemically. Whew. Now, the book suggests we don't need to memorize, like, all 118 elements to get started.
No, thankfully not. That would be A lot.
It highlights 12 basic ones we see all the time.
Yeah, really practical approach. Let's maybe run through them quickly.
Good idea. First up,
Hydrogen. Symbol H, element number 1. It's literally the most common thing in the universe, like 75% of all atoms.
Yeah.
And it's in almost everything essential. Water, organic molecules.
right. Number 1, that.
Oxygen.
Oh,
Element number 8, super important, bonds with almost everything. Forms water, oxides, and of course we need it to breathe. Vital.
can't live without it. Okay, next.
Helium. Number 2, second most common in the universe, mostly in the sun and stars, not much here on Earth, comes from decaying heavy metals. And it's so light and stable, it doesn't really form compounds.
Ah, the balloon gas. Makes sense.
Then carbon. See element 6, the backbone of life. All living things rely on carbon. Cells, organs, blood. About 20% of our body is carbon. It forms amazing chains and rings.
Crucial. Okay, who's next?
Nitrogen, N. Makes up most of the air we breathe. About 80% of the atmosphere is in euros gas. Pretty stable on its own, but it gets reactive when combined with other things, especially in fertilizers and explosives.
Then we have sodium.
Yep, sodium. It's metal, group 1. Quite reactive, so you usually find it in compounds like table salt, sodium chloride. Important for nerves and muscles.
And chlorine goes with it. Cl.
Often does. Chlorine Cl is a halogen gas, also very reactive, loves bonding with metals like sodium, used in bleach, disinfectant, salt.
Okay, keep them coming.
Magnesium. MaJ, another metal, alkaline earth group. Stable, but often more useful when bonded. Important for plants like in chlorophyll.
Aluminum. Al, sign down on that one. Foil.
Aluminum Al, element 13. Interesting metal. Pure aluminum is soft, but it forms a tough protective layer. Great for making alloys strong, but light. Think airplanes.
Right. Then sulfur. S.
Sulfur S, in the oxygen family, but it's a non-metal. Not super reactive normally, but can be explosive when heated with metals or gases. Think gunpowder, sulfuric acid.
Silicon. Si, like Silicon Valley.
Exactly. Silicon Si. Super abundant like carbon, but usually found bonded mostly with oxygen. Makes up sand, rocks. It's a semiconductor, not really a metal, vital for computer chips, also in glass, pottery, concrete.
Wow, does a lot. And the last one.
Boron.
Hey.
The only non-metal in its group, found in the Earth's crust, main part of borax. You know, the cleaning stuff.
Yeah. Okay, so those are the 12 basics. Hydrogen, oxygen, helium, carbon, nitrogen, sodium, chlorine, magnesium, aluminum, sulfur, silicon, boron.
Got it. And the book even had experiments using these.
It did. Simple ways to see chemistry in action. Soap making was one.
Soap. How does that work? You basically mix water, sodium hydroxide, that's lye, contains sodium, and some kind of oil or fat, which has carbon, hydrogen, oxygen.
And they react.
Yep, a chemical reaction called saponification happens. It turns the fat and lye into soap. But the key thing is you have to let it cure for ages, like 6 weeks.
6 weeks? Why?
Because the lye is really caustic, dangerous. You need to wait for the reaction to finish completely. So all the lye is used up, making the soap safe. Definitely requires patience.
No kidding. What about the other one? Slime. That sounds faster.
Much faster. Slime usually uses white glue, which has long molecule chains called polymers, water, and a borax solution. Borax has boron and sodium.
And mixing them makes slime.
The borax links those long polymer chains in the glue together, making it thick and stretchy. Instant slime.
Cool. And it mentioned keeping it in the fridge.
Yeah, good tip. To stop mold growing, which is, another set of chemical processes. Biology meets chemistry.
So even making slime is chemistry with these basic elements. Okay, this leads nicely into the periodic table. The book stresses how important it is for understanding structure.
Absolutely essential. It's like the ultimate cheat sheet for chemistry. It organizes everything based on properties and structure.
More than just a list of elements.
Oh, way more. The way it's arranged the rows, the columns, tells you so much about how an element will behave, how it will bond. The book's comparison to an ingredient list is pretty good. Knowing where an element lives on the table gives you its key characteristics.
Okay, so let's break down one of those boxes on the table. What info is packed in there?
Right, the element itself. You've usually got a few key things. First, the symbol, 1 or 2 letters, like H for hydrogen, Phi for iron. Second letter is always lowercase, important for formulas.
Got it. H-O, Phi, no.
Then, usually at the top, the atomic number. That's the big one. It's the number of protons. Defines the element. And in a neutral atom, it's also the number of electrons.
Protons, electrons normally. Okay.
Below the symbol, often the element's full name. Sometimes left off on complex charts, but usually they're on simpler ones.
And at the bottom, sometimes there's another number.
Yeah, the atomic weight or atomic mass. It's basically the average mass of an atom of that element. important for calculations, especially figuring out neutrons.
Ah, neutrons. How do we get that number again?
You usually subtract the atomic number, protons, from the atomic mass number, protons plus neutrons. The book used sodium, atomic number 11, mass about 23. So 23 minus 11 gives you 12 neutrons, roughly.
Okay, atomic number minus atomic mass. Wait, other way around. Atomic mass minus atomic number.
Right, mass minus number gives you neutrons. Remember, the mass number on the table is an average, though, because of isotopes.
Isotopes, different numbers of neutrons, right?
Exactly. Same element, slightly different mass.
Okay, so symbol, name, atomic number, protons, electrons, atomic mass for neutrons. Now, the table's layout. The rows and columns mean something specific. Periods and groups.
Correct. The horizontal rows are called periods. They basically tell you how many electron shells or energy levels an atom has.
Shells, like layers.
Kind of like layers or orbits where the electrons hang out. As you go down a row, you add another shell. The book mentions subshells within these main shells, S, P, D, F, G, that hold specific numbers of electrons.
Okay, so periods, a number of electron shells. What about the columns, the groups?
The vertical columns are groups. Elements in the same group have the same number of valence electrons.
Valence electrons.
Those are the electrons in the outermost shell. They're the ones involved in chemical bonding. So elements in the same group tend to react similarly because they have the same number of these outer electrons available to play with.
Ah, so group 1 elements all have one valence electron.
Yep. And group 17, the halogens, like chlorine, all have 7 valence electrons. Group 18, the noble gases like helium and neon, have a full outer shell, which is why they're so stable and unreactive.
So the table shows electron structure just by position. That's clever.
It's incredibly powerful. The book uses examples like oxygen, potassium, iodine.
Let's try oxygen. Where is it? What does that tell us?
Okay, oxygen, O. It's in period 2, group 16. Atomic number 8, mass about 16.
So 8 protons, 8 electrons, about 8 neutrons.
Check. Period 2 means it has 2 electron shells. Group 16 means it has 6 valence electrons in that outer shell.
6 in the outer shell. How many in the inner one?
The first shell only holds 2 electrons, so oxygen's electron arrangement is 2 in the first shell, 6 in the second outer shell. That's why it wants to gain 2 more electrons to get a stable outer shell of 8.
Makes it reactive. Okay. What about, say, potassium? K.
Potassium, K. It's down in period 4, group 1, atomic number 19, mass about 39.
Okay. 19 protons, 19 electrons, about 20 neutrons. Period 4 means 4 shells.
4 shells, right? And group 1 means...
Just 1 valence electron. Way out there in the 4th shell.
Exactly. The inner shells are full. 2 electrons in the first, 8 in the second, 8 in the third, and then that lonely one in the 4th. That's why potassium is so keen to lose that 1 electron and become stable with the full 3rd shell.
Reactive in a different way. Okay, one more. Iodine.
Iodine. Ion. Way down in period 5, group 17, atomic number 53, mass about 127.
Oh! 53 protons, 53 electrons, 127 minus 53 is 74 neutrons.
That's right. Period 5 means 5 shells. Group 17 means 7 valence electrons.
7 in the outermost 5th shell, needs 1 more to be stable, like chlorine.
Precisely. Its electron setup would be 2, 8, 18, 18, 7. You can see how knowing the period and group instantly gives you the valence electrons and a sense of its reactivity.
Yeah, the periodic table is definitely the key. Okay, so now we understand atoms and elements better. The book then talks about molecules and formulas, like HO.
Right. Chemical formulas. They're like recipes for molecules. HO tells you it's made of hydrogen, H, and oxygen, O.
And the little number, the subscript 2 after the H?
That tells you how many atoms of that element are in one molecule. So HO means 2 hydrogen atoms, and since there's no number after O, just 1 oxygen atom.
Okay, so PO would be 1 carbon, 2 oxygens.
Perfect. That's carbon dioxide. The formula is the molecule's ID card.
But why do they combine like that? Why HO and not HO? That comes back to bonding, doesn't it?
Exactly. It all comes back to achieving stability. That stable outer electron shell, usually with 8 valence electrons, the octet rule.
Like the noble gases have.
Precisely. Elements bond to get that stable configuration. Remember potassium with its 1 valence electron? It's unstable. It wants to get rid of that electron to have a full shell underneath, so it bonds readily.
By giving it away.
That's one way giving electrons away, or taking them from another atom. The other main way is by sharing electrons. These lead to the 2 main types of bonds the book discusses.
Ionic and covalent.
You got it. Ionic and covalent bonding.
Okay, tell me about ionic first. Giving and taking.
Yeah, essentially. One atom transfers 1 or more electrons completely to another atom. The atom that loses electrons becomes positively charged, an ion, or a cation.
Because it has more protons than electrons now.
Right. And the atom that gains electrons becomes negatively charged in anion.
More electrons than protons?
Exactly. Now you have these oppositely charged ions, and opposites attract. That strong electrostatic attraction is the ionic bond.
Like magnets clicking together.
Good analogy. The book uses table salt sodium chloride, NaCl. Again, sodium Na is group 1, has 1 valence electron and wants to lose. Chlorine Cl is group 17, has 7 valence electrons, wants to gain 1.
Perfect match.
It is. Sodium gives its electron to chlorine. Sodium becomes a positive Na ion with a stable outer shell underneath. Chlorine becomes a negative Cl with a stable outer shell of 8. They attract strongly, forming the salt crystal.
Okay, ionic electron transfer creates ions, attraction. What about covalent sharing?
Covalent bonding is all about sharing pairs of electrons between atoms. Nobody completely wins or loses electrons.
So they both get to count the shared electrons towards their stable octet.
That's the idea.
Yeah.
It's common between non-metal elements, like in gases or organic molecules. The book mentions 2 oxygen atoms bonding to form OROs.
Oxygen needs 2 electrons, right? It has 6 valence.
Correct. So 2 oxygen atoms can each share 2 of their valence electrons with the other one. That creates a pool of 4 shared electrons between them.
A double bond.
Exactly, a double covalent bond. Each oxygen atom now effectively has access to its own 4 unshared electrons plus the 4 shared electrons, giving both a stable count of 8 in their outer shell. They stick together because their nuclei are both attracted to that shared electron cloud.
Okay, covalent electron sharing to achieve stability for both. No ions formed.
Not in the same way. The overall molecule is neutral, though the electron sharing might be uneven sometimes, creating polarity, but it's fundamentally different from the full charge separation in ionic bonds.
Got it.
Yeah.
Transfer versus sharing. Now the last bit, creating formulas. How do we predict how things combine? Like why KO and not CO, though CO exists, right? Carbon monoxide.
CO does exist, yes, but CoRo is often formed under different conditions. The book tries to explain the drive behind formula creation. 2 main things: achieving that stable outer shell, usually 8 electrons, and the formula just represents the final ratio.
Okay. It uses carbon and oxygen again. Carbon needs 4 electrons, oxygen needs 2. How do they make it work?
Well, if just one C and one O try to bond, it's tricky. They can't easily satisfy each other fully just by sharing or transferring between the 2 of them.
Not stable, so they need more players.
Often, yes. The book looks at adding another atom. What if you add another carbon, making COO, to carbon monoxide?
How does that work?
It's complex bonding, but essentially involves multiple bonds allowing the carbons and the oxygen to share in a way that approaches stability for all 3. The book's explanation might simplify it a bit, perhaps suggesting one carbon helps stabilize the other before interacting with oxygen.
Okay, maybe a bit advanced. What about adding another oxygen instead, making CoO? That seems more common.
Co-ro, carbon dioxide, is very common. Here, the central carbon atom forms a double covalent bond with each of the 2 oxygen atoms.
So carbon shares 2 electrons with the first oxygen and 2 electrons with the second oxygen.
Exactly. And each oxygen shares 2 of its electrons back with the carbon.
Let's count. Carbon shares 4 total, gets 2 back from each, so carbon sees 4 plus 2 plus 2 equals 8 electrons. Stable.
Right. And each oxygen shares 2, keeps 4 of its own, and gets 2 from carbon. So each oxygen sees 4 plus 2 plus 2 plus 2 equals 8 electrons.
Just
stable.
Everyone's happy. CoO makes sense based on sharing to get 8 valence electrons.
That's the driving principle. Achieving stability dictates the ratios in which atoms combine, and thus the formulas we write.
Amazing how it all fits together based on those electron shells. And the book wraps up by saying, basically, don't be afraid to try things.
Yeah, it encourages that idea of trial and error, of experimenting. Chemistry is about understanding, but also about doing.
Okay, so let's recap this deep dive. We looked at matter anything with mass taking up space and its states. Solid, liquid, gas, and plasma.
Then elements, the basic building blocks and compounds, which are elements chemically bonded together.
Driven by atoms, the smallest unit of an element, made of protons, neutrons, electrons, and molecules, which are groups of bonded atoms.
We saw how matter changes physically, same stuff, different form, or chemically, new stuff formed via reactions, burning wood versus melting ice.
Right. And we met 12 key elements like hydrogen, carbon, oxygen, sodium.
And saw how the periodic table is this amazing map organizing them by atomic structure, revealing electron shells and valence electrons through periods and groups,
Which explains chemical bonding, ionic, transferring electrons, and covalent, sharing electrons, as atoms strive for that stable outer shell.
leading finally to chemical formulas like AgO or CoEro, which show the ratio of atoms needed for stability in a molecule.
It really does all connect back to those tiny electrons and their quest for stability.
Absolutely. And as the book started by saying, this isn't just lab stuff. It's cooking, breathing, rusting, living. It's happening all around us, all the time. Understanding these basics really changes how you see the everyday world.
It really does. Okay, so final thought then. We talked about carbon and oxygen making CO or CRO. If the arrangement of atoms dictates properties, what subtle differences in how atoms are arranged, maybe in more complex molecules using those 12 elements, could lead to drastically different substances or reactions?
Ooh, that's a great question. Isomers, structural differences. Yeah, tiny tweaks in arrangement can have huge effects on properties and reactivity. Definitely something to ponder.